Hello and welcome to the Summer Internship demonstration video. This internship has been a continuation of the second sem EL project, which is developing a novel algorithm for privacy preserving data publishing for multiple sensitive attributes. Mainly in the Summer internship, we have expanded on the front where we host the datasets on a public platform like GCP, Google Cloud Platform, and also run aggregate queries on the dataset to validate the anonymized data. So now without any further ado, let me show you the website that we have developed for the same. So as you can see here, this is the home page of the website. At the top is the title and the nav bar where we have added these cool hover links, and these help you to quickly navigate to any section of the website, and there's a smooth scrolling navigation to ease your experience. This is the front page where we have the carousel. It gives you a brief introduction about what the website is about. I'll give you a few seconds to read this. Yep. Here we have the dataset section of the website where we have briefly discussed the original table that we have received and the mask table produced after running our incremental diversity algorithm on it. So over here, there are buttons provided for each dataset where upon clicking on it, it will be locally downloaded to your system as a CSV file. Over here we have the query section where we have discussed 4 queries with various permutation and combinations of the attributes. Like here we get the data of the person who's employed in a state government and is a bachelor. Here we are getting the divorcee details, so on and so forth. And for each query there's an associated query button where if you click on it, you'll see the exact query run on GCP, which is right over here. And you also, after clicking the dataset button, after you run this query, the dataset that is produced after this query is run can be downloaded by clicking over here. And again, it is locally downloaded to your system. And over here, we have done comparisons of running the same query on the original dataset and mask dataset and discussed the results in the paragraph explanation over here. And we have done this for age, gender, and zip code quasi-identifier attributes. At the last but not least part of the website, we have the footer and about section where we have given the team member names, which is myself Hardik, Tanmay, Ashiq, and Raza. And we also have a project description section over here, briefly giving the project summary in a nutshell. And if you want to see how the website is built, the tech stack used, you can go to the GitHub page for this, which is private right now, but you can anytime access the link which is there in the readme section and see the website. The readme section also consists of the various links of all the datasets associated with this project, such as the query datasets, mask table dataset, etc., so on and so forth. This readme page is not available unless and until the repository goes public, which it soon will. This is the Google Cloud Platform bucket where we have stored all the CSV and dataset files associated with the project. Like here we have stored the comparison results, here we have stored the query results, here we have stored the mask dataset, and here we have stored the original dataset. Not to forget, we've also stored quasi-identifier and sensitive table dataset tables here too. So now let me give you a sample run of how the queries run. This is the bachelor and state government query that I first explained to you. And when I click on run, it generates the query result after running that query through the mask table dataset. And this is the result produced. You can even download it or explore the data for more exploratory data analysis. So now let me explain to you the tech stack that we have employed. We have majorly used HTML, CSS, JavaScript, and the JavaScript framework that we have used is React, which is mainly front-end heavy, front-end focused website framework, because most of the functionality that we had to use was front-end, like displaying and presentation of the work done, and the back-end functionality was little to none. So we decided to go with React. This is the app.jsx file, which contains all the components of all the sections of the website that you saw, such as the title and navbar, welcome section, the carousel, the smooth carousel, dataset, queries, comparison section, footer, etc. This is the title and navbar section, which contains the links over here, these top links. We have added the cool hover effect with this custom CSS code. And one interesting tweak that we have done with the project is we have made a query.js JavaScript file which basically contains a function that exports this query's list of JavaScript objects. This list basically contains of each query object with its associated details like query's ID, a query's title, statement, image, caption, explanation, and table link, so on and so forth. So now at any point of time, we can add or remove queries from this file, and it will dynamically update on the website. We basically use a dot map function in JavaScript to iteratively render the query to generate the query tag for each query object. In the further part of this video, you will get a detailed explanation of the incremental diversity algorithm and how we have stored a dataset in GCP and how the queries are run. Thank you.
Myself, S. Mohammed Ashiq, I will explain the incremental diversity algorithm. When we publish a data over the internet, utmost care should be taken that the data should be published in such a manner that it ensures privacy. The incremental diversity algorithm is able to diversify the data with multiple sensitive attributes and produce very less number of residue records. We are given with a data set of 5000 record which contains many attributes such as age, gender, zip code, education, etc. Here, age, gender, zip code are the quasi-identifiers, whereas marital status, relationship, and disease are the sensitive attributes. First of all, we have to import the microdata table in a standardized manner with the implementation of the nested dictionary. The keys of the outer dictionary is the record number which is unique for a particular record. The value of the outer dictionary is again a dictionary where the keys are the attribute names such as age, gender, zip code, education, etc. Whereas the values for the inner dictionary is the associated attribute value or the actual record associated with the attribute name. The second step is to diversify the microdata table. Before moving into the diversification, I want to show some of the code snippets which we have used in our program. The function get number of unique value will give the total count of number of unique value associated with the particular sensitive attribute. The function get value in equivalence table will give the total number of records present in the equivalence table. Equivalence table is nothing but a subclass of a microdata table. The function getParent will give the parent value of the primary sensitive attribute. Here the primary sensitive attribute is marital status. The function parents check will check if the parent is present in the particular equivalence table or not. The function getDiseaseParent will give the parent value of the disease sensitive attribute. The function disease parent check will check if the parent is present in a disease parent is present in a particular equivalence class or not. Now, totally 5 algorithms are designed to provide the intricate results. The first algorithm is based on the unique appearance primary sensitive attribute with few parent in the semantic hierarchical tree. Here, the first diagram is the semantic hierarchical tree for the marital status. The second diagram is the semantic hierarchical tree for the disease sensitive attribute. The first algorithm says that if in an equivalence class, suppose the sensitive value of one record is video, then no other records in that particular equivalence class should contain video as their sensitive value. The second algorithm is based on the unique appearance of parent in the semantic hierarchical tree consisting of fewer parents of parent for the primary sensitive attribute. In this semantic tree, the parent of video is unmarried. So in the particular equivalence table, no other sensitive values should be there whose parent is unmarried. To counter the problem faced in the algorithm 2, the algorithm 3 is based on the appearance of the parent in a semantic hierarchical tree consisting of fewer number of parents for the primary sensitive attribute at most twice. The primary sensitive attribute for a given parent can be at most twice. The algorithm 4 is the offshoot of algorithm 1 where where the primary sensitive attribute consists of many parents compared to the algorithm 1. The algorithm 5 is based on the appearance of a parent in the semantic hierarchical tree consisting of more number of parents for a primary sensitive attribute. In the hierarchical tree, when compared to the marital status hierarchical tree, the disease semantic hierarchical tree consists of more number of parents. Now, the function diversify records takes in five parameters as an argument. In the diversification of the microdata table, we create a temporary dictionary and we will pass all the sensitive values which does not fit in the current dictionary to the temporary dictionary. Then we iterate through the temporary dictionary and pick and place the record to the new dictionary. This diversification method is for the primary sensitive attribute. For the secondary sensitive attribute, tertiary sensitive attribute, and the quaternary sensitive attribute, we swap the values from the residue dictionary and the current dictionary because we have to make sure that the sensitive values are not repeating very frequently in a given equivalence class. The function get two tables will create two separate tables. One is quasi-identifier table and another is a sensitive attribute table. The sensitive count function for the sensitive attribute table which we have created, it contains group ID, the sensitive value name, and the number of times the particular sensitive value is repeated. The mask data. It is very necessary to mask the quasi-identifiers too. If the attribute is an age, we will generalize the age by giving them a lower limit and upper age limit. If the attribute name is gender, we will mask them but by not specifying their proper gender. If the attribute name is a zip code, we will mask the some digits of the zip code with the help of asterisk symbol. The get masked dictionary will return the masked dictionary table. The get time performance function will return the total time required to run the program. The function get residue percentage will give the total number of residue, the total number of information, the percentage of information loss. It is calculated by the total number of records present in the residue dictionary divided by the total number of records present in the microdata table. The get diversity percentage will give the percentage of diversity, which is the number of unique values for a particular for the particular sensitive attribute divided by the total number of sensitive values. Display performance function will display the performance parameters. Now we shall run the program. At first it will ask to enter the mode which you want to perform. The first mode is a test for a specific case. The second one is plot the graph. Plotting of graphs and the result section will be dealt in the later section of the video. I'll enter one. It will ask for the number of record. You can enter any number of records below 5000. I'll simply put 20. It will ask the value of k. I'll put 2. It will ask which algorithm you want to execute. I'll simply put 2. It will execute. This is the output. It displays the original microdata table for 20 records. It displays the modified microdata table. It displays the quasi-identifier table. It displays the sensitive attribute tables with the sensitive values which occur more frequently and their count. And it displays the masked microdata table where you can see quasi-identifiers are masked and generalized, and it gives the performance parameters. Here the code runtime is 20.02 millisecond, the residue records is 10%, and the diversity is shown to be 92.60%.
So now let's come to the research and conclusion topic of our program. The performance of the program is calculated by plotting out various graphs for various parameters. Total 6 graphs have been plotted using various parameters to obtain the best estimation of the performance of the group program. The following are the parameters of the graph plots. For constant value of k, we have plotted 3 graphs. One is records as residue percentage, the other one is records as time, and the third one records as diversity. For constant values of records, we have plotted another 3 graphs which are k versus residue percentage, k versus time, and k versus diversity. Each of these graphs have been plotted for 5 different algorithms. Marital status. In this algorithm, unique values of marital status are present in each equivalence class. Marital semantic tree 1. Here, unique marital parents are present in each equivalence class, that is, one married and the other one unmarried. Marital semantic tree 2. In this algorithm, in each equivalence class, only one type of marital parent can be repeated at most 2 times. In the relationship algorithm, unique relationships are present in each equivalence class, and in disease semantic tree, unique parent disease are present in each equivalence class. Now let's come to the first graph. The first graph is plotted for number of records versus residue percentage. Here we can see that the For Madel semantic tree algorithm, the residue percentage obtained is very high, while for disease semantic tree algorithm, the residue percentage obtained is very low. Hence, we can say that the best possible case here is the disease semantic tree. Here we get less number of residue percentage because disease semantic tree consists of large number of unique parents, hence lesser number of residues. The next graph is plotted for number of records versus time taken. Here we can see that the time taken for Mantis semantic tree algorithm is very high compared to the other algorithms for larger number of records. This is because Mantis semantic tree consists of lesser number of unique marital parents. Hence, more number of residues are obtained, due to which it takes more time to iterate through the residue list for the replacement of the records. Next graph is plotted for number of records versus diversity. Here we can see that a diversity of marital symmetry is very high, while the diversity of other algorithms are low. This is because the number of unique marital parents are lesser compared to the other algorithms. So less number of records will be obtained in the final modified microdata table. Next graph is plotted for k versus residue percentage. Here we can see that there is an incline increase in the slope of the curve for all the algorithms. This is because as number of k values increases, there will be less number of unique records. Hence, the more residue percentage increases. Residue percentage obtained for the marital symmetry is very high. This is because it has very less number of unique marital parents. Next graph plotted is for k versus time. Here we can see that as k value increases, the time taken for the execution of the program also increases. Here the special case which we can see is for the marital symmetry tree 1, where initially the time increases for a k value increase, but after k equals to 4, there's a decrease in the time taken because of less number of records. Next graph is plotted for k versus diversity. Here we can see that initially the diversity is very high for lower values of k, but as the k value increases, the diversity for almost all algorithm decreases. But only for the marital semantic tree, the diversity increases because of less number of unique parents. Hence, more residues are obtained, which will result in less number of records in the final modified macrodata table. Now let's see the comparison between the LE diversity algorithm and our incremental diversity algorithm. The LE diversity algorithm uses the primary sensitivity attributes with less number of parents, such as marital status. Our incremental diversity algorithm makes use of the primary sensitive attribute with more number of parents in the semantic hierarchy, such as disease semantic tree. Our algorithm also performs the incremental diversification for secondary, tertiary, and quaternary sensitivity attributes, while the early diversity algorithm focuses only on the primary sensitivity attributes. The time for, performance for our incremental diversity algorithm is faster than the early diversity algorithm with less number of residue percentage. Here are various graphs plotted for the comparison between the early diversity algorithm and our incremental diversity algorithm. Here we can see that the time for execution of the program is more for the early diversity algorithm, while the time taken for incremental diversity algorithm is very less. The residue percentage obtained for incremental diversity is very low as compared to the early diversity algorithm. One of the lesser residue records for the incremental diversity acts as a double-edged sword because of lesser residue percentage. Hence, the diversity obtained is also very less compared to the early diversity algorithm. Here we can see that the residue percentage obtained for early diversity is very high as the k value increases. Here, the time taken for incremental diversity is initially low for lower values of k. Here, as told before, the diversity for a early diversity algorithm is greater than the incremental diversity. Now let's see the software tools which are used for our program. We have used pure Python programming language for the coding of our program. Here, CSV files are used for the dataset which contains the records of each person details. Math module is used for performing various mathematical functions. Here, time module is used for obtaining the time taken for the execution of a program. Matplotlib.pyplot module is used for plotting graphs for the various parameters. Tablet module is used to align the records in the form of proper tables.
Hello, I am going to tell about the steps of creating buckets in GCP as we have used GCP to store our dataset. We have written a paper in which we present a methodology for storing datasets in GCP. So the method is to create the GCP account and then go to GCP. So this will be the page. So click on view all products. This is the first step. Select storage, then select the create button and then write the name of the bucket in this format. Then choose this option, control access, then select fine grain. This fine grain we have to select in access control. So select, then click on the bucket name, this one, then upload files. So click it, then click the three dot menu here and then click the edit access. Then each step is click the add entry and fill the following details. Fill it entity 1 public, name 1 all users, access 1 reader, and entity 2 we can neglect fully. Then copy the link available here, this copy URL. So copy the URL and then you can share that link to the dataset. So now let me little discuss about the results of the queries. We have written another paper in which we discuss about the results obtained after running a query on the mass data table obtained from the original data by implementing incremental diversity algorithm. So we'll see one example of the result. So when we run a query like this, select lower age, upper age, where education should be bachelor's and employment state government, and order by group ID. So it will by ascending order of the group ID. So this is the result we get, where education is the bachelor's and employment is the state government.